we are going to see matrix chain multiplication. So let us see first today's outline. First we are going to see matrix chain multiplication problem. Then we will see how matrix multiplications and dimension does matter. Then we will see optimal parenthesis structure of matrix chain multiplication. Finally, we will see an example of how to compute optimal cost of matrix chain multiplication. For the rest of this session, we are going to refer our matrix chain multiplication problem as MCM problem. We are given a sequence of n matrices A1, A2, A3 and up to An, which are needed to be multiplied in the same order. That means the order of multiplication of matrices should not be changed. They should be as it is. Next, there do exist multiple orders of multiplication to compute a same product. That means I want to at the end compute a product of A1 with A2, A2 with A3 up to An. But there do exist multiple orders of multiplication. Now what do we mean by that? So let us take an example and understand what do we mean by order of multiplication. Say for example, we want to multiply 4 matrices A1, A2, A3 and A4. Now these 4 matrices can be multiplied in different ways. First I can multiply A1 and A2 and compute my partial result. Followed by I can multiply A3 with A4 and compute another partial result. And I will multiply them in a same order of their precedence. That means partial result of multiplication of A1 and A2 will be multiplied with partial result of A3 with A4. So this is the order in which we are going to multiply 4 matrices. But that is not only the same or single method of multiplication. I can either multiply A2 with A3, then I can multiply A1 with this partial result and the complete partial result with A4 also. That means the order in which I am going to multiply is A2 with A3, then A1 with partial solution followed by A4. There do exist another way. That means I can either multiply A2 with A3 first and their partial result can also be get multiplied first with A4 and ultimately I can multiply A1 with this partial result. That is also acceptable. Or I can do another thing also. That means A1 can multiply with A2, their result can also be multiplied with A3 and the result can be multiplied with A4. So for any given series of matrices, if I want to compute their product or a multiplication, there do exist different orders in which I can multiply. So here one more example, that means I can start multiplying from the last also. It is also possible that A3 can be multiplied with A4 and their result is getting multiplied with A2 and their result is getting multiplied with A1. So here, what is our problem? Our problem is to find an order out of these 5, right? So these are not only the 5 ways with which we can multiply them. There do exist different orders. But what is the order in which it includes minimum multiplication or minimum number of operations that will be incurred? What do we mean by multiplication dimension? So let us consider we have 2 matrices A and B, and we need to multiply them. So number of scalar multiplications are R1 into R2, C1 into C2. Now what do we mean by this? Our matrix A is of dimension R1 cross C1 and matrix B is of dimension R2 cross C2. And if we want to multiply them, it is one prerequisite or a condition that we must satisfy, that the column number of first matrix should be equal to row number of another matrix. Unless and until this condition is not satisfied, we will not be able to multiply these two matrices. So the condition required to satisfy here is C1 should be equals to R2. Then if we multiply these two matrices, what will be the dimension of resultant matrix? The resultant matrix will be of dimension R1 cross C2. Yes, the resultant matrix will have number of rows that is equivalent to first matrix and number of columns which will be equal to second matrix. We will take element from first row of first matrix and element from column of another matrix, and we multiply them element by element and altogether sum them up. But here, how many multiplications will be done if we are multiplying a complete 2 matrix? So number of multiplications that will be done or number of operations that will be performed will be R1 cross C1 cross C2, or I can say R1 cross R2 cross C2. Now what is optimal parenthesis structure? So again we will take an example and see what are the optimal parenthesis structure and how it affect my order or times of multiplication. So there are three matrices A1, A2 and A3. Matrix A1 is of dimension 5 cross 4. That means it has 5 rows and 4 columns. Second matrix A2 is of dimension 4 cross 6, 4 rows and 6 columns. And third matrix A3 is of dimension 6 cross 2. That means 6 rows and 2 columns. Obviously, as you can see, if I want to multiply A1, A2 and A3, between A1 and A2, columns and rows respectively should be equal, which you can see the columns of A1 is 4 and rows of A2 is also 4. Again, between A2 and A3, columns of A2 is 6 and rows of A3 is also 6. So I can easily multiply them in an order of A1, A2, A3. So let us see first approach, where I first multiply A1 with A2 and the partial result will again get multiplied with A3. So while multiplying A1 with A2, my 5 cross 4 matrix is getting multiplied with 4 cross 6 matrix. So how many scalar multiplication will be there? There will be 5 into 4 into 6, that is R1 into C1 into C2. That many multiplications will be there. So in total there will be 120 multiplication of scalar size. And after multiplication, whatever the matrix, resultant matrix we will get will be of dimension 5 cross 6. Then I have to multiply this 5 cross 6 matrix with A3, which is actually 6 cross 2 matrix. So 5 cross 6 matrix is getting multiplied with 6 cross 2 matrix. So here scalar multiplications will be 5 into 6 into 2, which is equals to 60 scalar multiplication. And what will be the resultant dimension of my matrix? The resultant dimension of matrix will be of 5 cross 2 size. So in total, how many scalar multiplications we have done? We have done 120 plus 60, that is 180 in total scalar multiplication to get our final result. The second approach of multiplying matrix, that is we are first multiplying A2 with A3 and their partial result is getting multiplied with A1. So here while multiplying A2 with A3, A2 is of 4 cross 6 which is multiplied with 6 cross 2 matrix. So number of scalar multiplication in this case will be 4 cross 6 cross 2, that is 4 into 6 into 2, total 48 multiplications will be there. And the dimension of the result or the partial result will be of 4 cross 2 size. Then this result is getting multiplied with A1. A1 is of dimension 5 cross 4 and here the partial result is of 4 cross 2 size. So number of total scalar multiplications are 5 into 4 into 2, which is equals to 40, and the resultant matrix will be again of 5 cross 2 size. But how many scalar multiplication in total we have performed? In our second approach, we have performed 48 plus 40, that is equal to 88 scalar multiplication. So whether we are following approach 1 or approach 2, our result will be same. That is a matrix of 5 cross 2 size and their element will be also same, whether we are going with either approach 1 or with an approach 2. But where is the difference that lies? The difference lies in the order of multiplication, that is the structure of parenthesis. In our first approach, we have put parentheses across A1 and A2, while in second approach, we have put our parentheses across A2 and A3. So their order is can either increase your number of multiplication or they can decrease your scalar multiplication. So obviously, which one is optimal? The less number of the operations, the faster the output. That's why we are here interested in finding those parenthesis structure in which scalar multiplication will be minimum or the least. Now we will see the memorization function of finding optimal cost. We will prepare a table M whose element or ij cell value is calculated as minimum of m of ik plus m of k plus 1j plus p of I minus 1 ik into pj, where I is less than or equals to k is less than or equals to j minus 1 and m of I is equals to 0. Now we will see how to compute that particular table and how to find optimal parentheses with the help of example. So this is my example where 4 matrices are given: A1, A2, A3 and A4, and their dimensions are 5 cross 4, 4 cross 6, 6 cross 2 and 2 cross 7 respectively. Now these are going to get multiplied as in order of A1 into A2 into A3 into A4. And what is the optimal cost of multiplying these matrices? That means I have to find out how many multiplications in total we have to do in order to perform or to multiply them. So here we have calculated or created our P vector. Now this P vector is calculated as L shape from your dimension. As you can see, the topmost value of dimension is 5, then we have 4, 6, 2 and at the last 7. That is from P0 to P4. As you can see, there are only 4 matrices, that's why my n is equals to 4. Now my table M is created as in following format. Now as you can see, in my first row there are 4 columns. In my second row there are only 3 columns. In my fourth row there are only 2 columns and in last row there is only 1 column. So if n is equals to 4, we will start preparing 4 columns in my first row and there will be 4 columns. In last row we will have only 1 column. Now how we are going to number them? My rows are numbered over the right hand side and columns are numbered over the top side. Rows are actually traced using variable I and columns are traced using variable j. Now these all elements are going to get filled up. Now as you can see, the highlighted cells, that means we are skipping the last row and first column, that will be our another table, that is S table. So we are going to fill M table and S table simultaneously with the help of only one calculation. So let us start filling them. Our P vector is ready and M and S table is already created. Note carefully that in S table there is not first column and there is no fourth row. Alright, so let us start for Mi, I, where row number is equals to column number. First thing, before we proceed, I will tell you how we are going to fill up this particular table. The table is going to get filled up in a diagonal section. I's value is 0. So we will do m1, equals to 0. 2, 2 is also 0. 3, 3 as well as 4, 4 is also 0. So values of zeros will be now here filled up. Now we will take or we will fill up these cells diagonally. So we will start from top right hand side corner and fill them up diagonally. So from very top, for any cell in this table, we have formula m of ij is equal to minimum of m of ik plus m of k plus 1j plus p of I minus 1 into pk into pj, where I is less than or equals to k is less than or equals to j minus 1. So let us fill them up one by one. Cell number 1, 2. We are currently working in row 1 and column number 2. So my k value must be lie between I and j minus 1. As you know, i's value is 1 and j minus 1 is also 1. My k's value should be equal to 1 only. That is, my k is equal to 1. So I equals to 1, j equal to 2 and k equal to 1. These values are going to get substituted in our above formula. So then this above formula, it will become m of 1 comma 2 is equal to minimum of m of 1 comma 1 plus m of 1 plus 1 comma 2 plus p of 0, p of 1 and p of 2. So it will be calculated as minimum of 1 comma 1 is 0, 2 comma 2 is 0, 5 into 4 into 6. So that will be calculated as minimum of 120. As there is only one number and whose minimum has to be taken out, the number will be itself minimum value. So from set that there is only one element, the element itself is minimum. So this 120 value will be filled up inside table. We have to also fill up our S table. So the value we have filled in a cell number 1 comma 2. So also in our S table row 1 column 2 cell, we are going to put k's value whose value is being selected inside M. So for k equals to 1, minimum value is turned out to be 120. That's why k equals to 1 will be filled up inside my S table. So that k equal to 1 is being filled up. Now we will again work for another cell. That is the cell where I is equal to 2 and j equals to 3. Row 2 column 3 cell. That means my k should be between I and j minus 1. That is between 2 and 2. So obviously k's value is equal to 2. Now let us fill up I equal to 2, j equal to 3 and k equal to 2 in our formula. That turns out to be m of 2 comma 3, minimum of 2 comma 2 plus minimum m of 2 plus 1, that is equal to 3 comma 3, and I plus 1, I minus 1, k and j, that is equal to p1 p2 into p3. Now p1 p2 p3 is 4 into 6 into 2 and m of 2 comma 2 and 3 comma 3 is 0. So the resultant value is 48. So minimum of an element 48 is 48 itself. So 48 is the value that we are going to put inside M table, and for this 48, for which value of k we have chosen this value? For k is equal to 2. So this value is going to get filled inside my S table. We will work in the same fashion for the next diagonal element, that is row number 3 and column number 4. Obviously k's value will be 3 in this case, and it is calculated as m of 3 comma 3 plus m of 4 comma 4 in plus p2 p3 and p4. So that is equals to be minimum of 84, which is equal to 84 itself. So value 84 is being filled, and for k equals to 3 value we have computed the result. So that 3 will be placed inside my S table. Again, after one diagonal is completed, we are going to shift upward towards our diagonal. So now we are going to fill up the upper diagonal, and we will start from our very first cell. So next element that we are going to put is row 1 and column 3 value. So here k's value is between I and j minus 1. As you know, i's value is 1 and j's value is 3, j minus 1 become 2. And k is greater than or equals to 1 and lesser than or equals to t. So there are two possibilities of k. K can be either equals to 1 or k can be 2. So here we have more than one values of k. So here it will become m of 1 comma 3 is equals to minimum of 1 comma 1, that is I comma k, and k plus 1j is m of 1 plus 1 comma 3, that is m of 2 comma 3, and last term will be p of 0, p of 1 and p of 3. And we will put comma and select k is equal to 2 and rewrite the complete term, that is m of 1 comma 2 plus m of 2 plus 1 3 plus p0 p2 into p3. So here the first term is considered with k is equal to 1 and second term is considered with k is equal to 2, because there are two possibilities of k. K can be either 1 or it can be 2. Values are computed as per the cell value. M of 1, 1's value is 0. M of 2, 3 is 48 that we have just computed, and P0, P1 and P3 is calculated from our P vector, that is 5 into 4 into 2. While working on another term, m of 1, 2 is looked up inside my m table, that is row 1 column 2 value, which is equals to 120, plus m of 3, 3 which is equals to 0, and P0, P2 and P3's values are 5 into 6 into 2. Now these values are getting calculated. So we have two values inside our minimum function. First value is 88 and another value is 180. The minimum value that we have to select is 88. Now pay attention over here. 88 is my first term and my first term is written for k is equals to 1. So while we are writing 88 in our table M, which value we are going to write inside my S table? The value minimum for which we have a particular k. So for k equals to 1, my term is actually minimum. The first term is actually written using k equal to 1 and second term is written using k equals to 2. That's why first term is come out to be minimum. So I will write down k equal to 1. The one entry of k is made inside my table S. Now let us work for another cell. That is a cell number row 2 column 4. So k value must lie between 2 and 3. So k can be either value 2 or it can be value 3. That's why we have two different values of k. So we will write the minimum inside term, the term which is inside minimum function, using using k equal to 2 and second term will be written using k equals to 3. So this is equal to m of 2, 2 plus m of 3, 4 plus p1 into p2 into p4. And second term is m of 2, 3 plus m of 4, 4 plus p1, p3 and p4. That is equals to minimum of 84 plus 4 into 6 into 7 and 48 plus 4 into 2 into 7. Now there are two different values inside my minimum function. The first term is 252 and the second term is 104. Final value is equal to 104. But can you tell me for which value of k this 104 is turned out? For k equals to 3, we are going to write 104 in our table M and k is equal to 3 in our S table. So this is my completion of second diagonal. Now in my third diagonal there is only one cell. So we are actually at cell number row number 1 and column number 4. Here k is equal to or k's value is lying between 1 to 3. K's value can be either 1 or it can be 2 or it can be 3. So as you know there are three different values of k for which I have to write down three terms inside my minimum function. First complete term will be written using k equals to 1. Second, the same term will be rewritten as k equals to 2 and for third term I will consider my k is equal to 3. So this is my first term, that is with k equals to 1, the second term with k equals to 2 and third term using k equals to 3. So their values are going to get generated. So there are three values 244, 414 and 158. So the minimum value out of these three is 158, which is for k equals to 3. So here 158 entry will be made and this is my third term and third value of k is equals to 3. So a k's entry will be inserted inside S table. So this is what we have done. So what is our optimal scalar multiplication or optimal cost of multiplying matrices A1, A2, A3 and A4 that were given in original problem? So here the final answer, we have to make 158 scalar multiplication to generate our answer.